Hi, stream. How you guys doing?
Hello and welcome back to Calculus 3 for one last time. This is it, Green's theorem. We're going to look at the what is also known as the fundamental theorem of line integrals, by calculus for line integrals. We have two versions. There is the circulation form of Green's theorem, and then there is the flux form of Green's theorem. So we start with the circulation form. Here's the theorem. Let C be a simple, closed, piecewise, smooth curve oriented counterclockwise that encloses a connected and simply connected region in R in the plane. So you know all those words that we defined over the previous two classes are now mushed in one definition. So here we go. Let C be a simple, closed, piecewise smooth, curve oriented counterclockwise that encloses a connected and simply connected region R in the plane. That's how you write that. Assume F is the vector field, right? Where F and G have continuous first partial derivatives in R. Then, and here we go. The integral on the closed curve C of f dot dr is the integral on the closed curve C f dx plus g dy. You are hopefully remembering circulation from last class, which is equal to the double integral over the region R, the one that was enclosed, of dg dx minus df dy dA. Now, in case you are freaking out now, that on the left-hand side you have a single integral and on the right-hand side you have a double integral, and how, comma, the hell, comma, are these two things equal to each other? I will remind you that the left integral does not contain derivatives within the integral and the right does. So one layer of integration will cancel with derivatives, leaving exactly the same amount of integrals. So dimensions of the both sides are actually the same. It is not intuitive when you look at it because you have one integral on the left end, but then also depending, you can look from the other perspective and say, you know, you have a line integral on one side which calculates the area of the curtain, writes its area. You also have the area on the other side. So that's also that dimensions match. solving this integral is just you know, plug and play, right? Plug and pray, I guess. You know that the vector field is given to you. You have your f, you have your g. There in terms of x and y. Partial derivatives, subtract, and you're done, right? The trick is to know how to set up the integral limits looking at the region. And the region is going to be a triangle, is going to be a square, is going to be a circle, is going to be something that you need to work with, whether it's rectangular region, easy, right? You put numbers all around. If it's not rectangular region, maybe you will be so unlucky that you run into a problem that has to be converted into polar coordinates and then go from there because it was a circle or a flower or something, right? So this part here is dealt with your skills from 13.1 and 13.2 and possibly 13.3 with polar coordinates. So the integration and setting it up. The 14.4 is the equivalency between the line integral that is happening on the closed curve. 14.2 is introducing you to the line integral, and the line integral, most of the examples that we did were on the line segment, or none of those curves that we did were closed. Can we use it to solve? Sure, but then you have to parametricize and have that huge integral and deal with a whole bunch of stuff. If these conditions are met, then this theorem applies, and it's a shortcut to solve the problem. So, and that's what we are all about in math. We would like to be as lazy as possible, do as little work as possible. So investing time to learn one more theorem that cuts out all this insane work. Every problem that we do here can be done by 14.2, except it's going to be longer and much more painful. And I encourage you to try that, right? So take any problem that we solve here and just unleash methods from 14.2. It will be more work, but you will get the same answer. So this is designed to significantly cut your computation time. And now, you know, there's never free lunch. You will have to deal with setting up the integral, looking at the region, and the region is going to be bound by the closed curve C. Square, rectangle, rhombus, parallelogram, triangle, circle, whatever it is, it has to be completely enclosed into it. This, if any of these conditions fail to apply, theorem immediately fails to produce the answer. You will have to go back and use 42 to solve that integral. So if the line is not smooth, that means it's not differentiable. Clearly this part can be done. If the curve is not closed, then you don't have a region, you can't set it up because the region is now infinite and this immediately blows up. So any one of these words that are here, if you miss any of the conditions, then this immediately doesn't apply. So it either explodes or it gives you the wrong answer. So let's take a look at the example of this. This part over here has a name. I almost forgot. This is called the two-dimensional curl. And if curl is 0, then the vector field is irrotational. Because curl, right? Curls, curling. So it is, I mean, words that are used, right? So if curl of f equals 0, the vector field is irrotational. What happened?
What's the
Curl F is like writing sine of x, if you're asking about that. This curl of F, it's like the operator on F.
curl of that?
Yeah, if curl of the F, yes, you literally write curl F. It's like sine x or ln x, or right? So curl F equals 0, and F is your vector field. So if curl of F is 0, then the vector field F is vector field F. Here you go. Is called irrotational. So we already did the line integral for rotational vector field, right? We had the negative y and x. We can unleash the green theorem upon that for the unit circle and get the same answer as we did before, which is 2 pi. We better get the same answer, because this theorem is just supposed to have much less work. Over there we had to get the vector r, which was parametrization, then r prime, then magnitude of r prime, then put all of that in the integral and work it out. And now you'll see it's going to be much faster than that. But again, all the conditions have to apply. So circulation, let me see. So vector field F, which is what we did before, is going to be negative yx. We're using the same problem like in 14.2. And we are going to be on the unit circle x squared plus y squared less equal than 1, which encloses the region. Region is connected because it's one piece. It's simply connected. There is no holes in it of any kind. And the counterclockwise rotation, if you pick x equal cosine t and y equals sine t, we experience counterclockwise rotation. So all of those things are at play. We have everything everything there. So now what do I do? All I need to do is I need to compute the curl of this, and as soon as I compute the curl, I just integrate that on the region. The region is a circle, so clearly we're going to use polar because that's going to be a joke. And well, let's just do. So this is F, this is G, right? So curl. I don't know why I'm screaming. Curl F. Yeah, well, curl F is fine. You will see much more of that in linear algebra, right? Yeah, there will be more notations like this, so enjoy it. Curl of F, right, is going to be our dg dx, so partial g partial x. So partial g partial x is 1 minus partial f partial y, which is negative 1. Curl is 2. So I am setting up a double integral, and I am integrating 2, and I hope you remember the string for the polar integrals, which is r dr d theta. We are using the unit circle. Radius goes from 0 to 1, and the theta goes entire circle 0 to 2 pi. So when I integrate this, I get r squared from 0 to 1 d theta. That's going to be 1 minus 0. Integral of 1 is theta. Plug in 2 pi, and there is your 2 pi. So when you compare this amount of work to what we had to do in 14.2, this is why, as you can see, we did not involve parametrization here at all. We just flew right through. Now, circle is smooth. It's differentiable. It is smooth means differentiable, right? So there are no sharp corners and edges and cusps that make function not differentiable. It is oriented to the counterclockwise, right? The region, which is the inside of the circle, has no holes. It is one piece. So all of those components are prerequisites for you to be actually able to apply Green's theorem. You can also try this to compute on the radial field, and you must get what? 0, right? Because the radial field has no rotation on it, which means that the curl of the radial field must be 0. And if you look at it, right, radial field is xy. When you find partial derivatives, it will be 0 minus 0. And that gives you 0 to feed into integral, so the answer is 0. So everything that we did before still works. This is the shortcut method that will deal with problems that have closed curve C, which is why you have this circle around the integral. This circle around the integral signifies that C is a closed curve, and it has all of those conditions that you have to check before you unleash this theorem. So it's nothing special. You know, don't let notation intimidate you and then you say, well, I can't figure this out. It's nothing special. If you understood 14.2, this is going to take a very small amount of problems and deal with them, right? Because any type of disconnected region or line segments or anything we did, actually, problems, this won't work. So I would like to give one problem for you to practice your plug-in skills. So here's a beautiful problem. Vector field is given as negative 3y, comma 3x. That's your vector field. And your region R is a triangle with vertices zero, 0, 1, 0, and 0, 2. Draw the region because you need to set up the integral later. Right, those double integrals. So this is technically 13.2 to set it up. Calculate the curl, put that in the integral, and then deal with the region looking at the graph. This is on the tomorrow's test, this problem. 100%. It's a learning outcome. It must be there.
This exact problem? With the numeric values?
Yeah, I'll put 5y.
So 5. 5y instead of negative 3y, right?
Yeah. Something. I don't leave the room before posting it. I believe I posted everything to 14.2. 14.4. I said I believe I posted everything to 14.2 on the notes.
Oh, no.
I need to post 14.3 and 14.4.
It says in the document that there's guidelines.
Two minus 2x is the slope.
I think I'm wrong. Yeah. I have another, but I think it's really clean. And
What are you talking about? -3 minus 3.
because I updated it, so I have everything. All my data.
Oh, it's G first.
So I can't wait. Stuff like this. I haven't played month.
Derivative of
It's
derivative of f with respect to
break
y.
now. Upgrade the phone and then I'll go back and forth. I've been on the grind for 2 years now. I haven't spent a penny for buying anything. I just keep I did all, grind. So I don't see me going from 0 to a hotel again. Because I started this, I believe, 2 years, 1 year or something like that. And I'm one of the I did really well studying and a hard way to get where I am, being that I'm years behind. I started from day 1 and now, level 1. I feel very, very confident, very happy, but I don't think starting from scratch will take me. Now all these people have like 15 Smurf accounts and those engineered plans. Okay, let's take a look because after this we have one more to look at. So we start from 0, 0, 1, 0, 0, 2. So this is my region R, Alex, okay?
Yeah.
I guess it's the end of the semester and no one cares. People gave up. So computing the curl of f, the curl of f is going to be partial g partial x. Partial g partial x is 3, and then minus, we have -3, it's 6. So double integral over the region R for 6, and now we are just going to use dr, dx, dy, or dy, dx. I'm going to use dy, dx. So dx is the main, which means goes from 0 to 1. Oh, come on. And y is going to go from 0 to the line over here, and line is 2 minus 2, yes, 2 minus 2x. The slope is negative 2, and the y-intercept is 2. Awesome. So all we need to do is to integrate this. So this is technically, most of the problem is actually dealing with the chapter 13, 13.1, 13.2, 13.3 to set up and evaluate the double integral. Alex, please look forward, because you're going to strain your back, man. Just sit straight. I don't want you to injure, because we don't have any registered nurses in this class. Like when I teach algebra, usually I have at least 2 or 3 students who are in a nursing program, and at that point I really don't mind people sitting like that. But then, you know, here it's like all STEM, and if you are to just fall over, you'll probably just bleed out. Because I don't think anyone here knows how to help. Like, you know, it's not going to help out with him bleeding out. It's, you know, that's if you pull him out of the pool, but he doesn't go to the pool. So yeah.
George was leaning back in his chair, but there wasn't a desk behind him, so he almost fell over.
Yeah, see, it's very dangerous. So we should all face forward at all times, just in case. All right, great. What was I doing? Oh yeah, the integral. So we have a 6y, so that's going to be 6 times 2 minus 2x, and then who cares about the 0? Which is, we can kick out 12 in front of the integral and integrate 1 minus x, dx, from 0 to 1. Yay, I know. Say with me, thou shalt not pass. Gonna be there like a Gandalf on the, you know. It's like there's gonna be one special exam with the Gandalf meme in the front. All right, so what do we have? We have x minus x squared over 2 from 0 to 1, and that will give us 1 minus a half. That's it, yes, there's a 12 there. So answer is clearly 6. There's a 12 there. Keep talking.
I mean, we only got 2 days of class left. You can still break your streak of not punching us.
All right. So the next part is going to be the flux version, and the flux version will involve divergence. Please connect the words with curl and rotation and irrotational, and then radiating out, which is a radial field, and divergence, because you have, let's say, take the sun as the source of energy, everything diverges away from, right? The sun gives off the X radiation, the fusion within the sun gives off X radiation, which goes away, diverges away from the sun, right? Any 2 rays diverge from each other. So now when I write the Green's theorem for the flux version, you will have the outward flux, and the piece inside will be called divergence. So the one with partial derivatives. The conditions are the same, so I'm not going to write all of the 6 lines again. Same conditions. As in circulation form. All right, so what do we have? We have that the integral on the closed curve F dot n ds is going to be the good old outward flux f dy minus g dx, which is double integral over the region R. And here we have the divergence, partial f partial x plus partial g partial y dA. This guy is known as the outward flux. And this puppy over here is called divergence. And we are going to write the similar statement. If your divergence is 0, that means that the region where your vector field is source free. Source is the sun, all right? So if the divergence is 0, that means that nothing radiates out. If you have a circular vector field, it doesn't radiate out. The stuff moves in the circle. Nothing goes away. So we're going to say that, well, this is 2D divergence. There's also 3D and stuff. Gotta look at the future lectures past this one. If divergence of F, here's your notation, Evan, right? Div F. Divergence of F equals to 0. Region R is source free. That means there is no source in that region. Immediately think of a sun. So the clear example here must be a radial field, which gave us 2 pi earlier in 14.2. We can start with that as the introductory example. We look at the radial field. We know we have to get 2 pi because that's what we got yesterday. So a radial field F, which is given as xy. It's the simplest radial field you can get. On your curve C, which is the unit circle, still a good old unit circle. And we compute divergence first. Divergence of F is the partial F partial X is 1 in this case, plus partial partial G partial Y, which is 1. So we get that divergence is 2. We will set this in the, again, polar coordinates integral because we have circle as C. So you saw me earlier, if I have a square or a rectangle, I use X and Y. If I have a circle or a flower or annulus or cardioid, I will be using polar coordinates. That should be common sense by now. Our radius is 0 to 1. And 0 to 2 pi, it's the entire circle. So the same story. We have 0 to 2 pi. Integral over here is r squared, computed from 0 to 1 d theta. That is just going to be integral 0 to 2 pi of d theta, which is theta from 0 to 2 pi is 2 pi. Extremely quick and simple to compute, but again, you have to make sure that all of the conditions are met. If any of the condition fails, it's not smooth. If it's not smooth, you can't take derivatives. That should be right. You can't have the absolute value there. Absolute value of x is not differentiable at 0, right? Any vertical asymptote is not differentiable at that value, and so on. So there's a lot of different ways to get the cusps and things in so that this doesn't apply. we are going to take a look at the example from exercises from homework. And I'm not gonna stick with the triangle, let's try something else. Oh, perfect. So here's a little spicier example. Try this one on your own first, and then this is problem 27. Your vector field F is given as 2xy and then x squared minus y squared. And your region R is bounded by y equals 2x minus x squared and y equals 0. So as you can see, it's a parabola above, right, and the x-axis, but you'll figure it out. You need that as a region, right, to set up the limits. That's what it worked out to be.
Okay, I wasn't sure if I was just messing up or that was what it actually turned out to.
So what do we get? What's the final example like this? Like
Okay, I'll do my.
we'll talk about that. Oh, that's right. It still has that. Yeah, it is. What are we getting? What are we getting? Zero. Is it? Yeah. Wait. Wait, what does that mean? That means source. Like the source, please. So there's no source. R is source free. Well, that's contractive. This is not the first time I'm doing this. I have a bunch of problems. Y minus. I've seen many times, especially. Hey, buddy. Can be done. No, wait, never mind. I'm being done. Yeah, that's zero. What's the difference? We're like probably 100% sure. That's zero. It's zero, right? Okay. All right. Wait, you look at a problem, you know it's zero, right? Yeah. There's source. No. Look, 2y minus 2y. Yeah. Divergence is zero. Done. There's no source and no flux. Nothing radiates. So the first order of business is to compute divergence of F, and that's going to be 2y minus 2y equals to 0. Double integral of 0 dA is equal to 0, and we're done.
How do we know when to use just the normal Green's theorem equation for the flux?
depending on the problem, the vector field.
I believe it was
Because, as you can see in this case, right? In this case, you don't have a source, so divergence over here is not not giving you anything. It's the application that guides what you are supposed to. Right? If you have a hurricane, you are not computing anything with the flux. It's a rotational field, right? I mean, to answer your question in the lowest possible form is you read the problem and it says use the circulation or use the, right? But I don't like that, right? Because ultimately you have to use this, and if you don't understand it, then it's a trouble. Technically, well, since you are all disappointed in the flux problem, let's do another one. I was trying to stay. Oh, actually, we can do this one, right? Or can we? All right, let's try next one, and then talk about the final exam. Yay.
wait a minute. Hang on.
So what are we having here?
Zero.
Well, I got 0.
0?
I got 0.
Why you got 0?
I mean, it's 2x. I got 2x.
That's 2x.
Yeah.
2x. Okay. So then what happens?
You integrate that.
We integrate this. Now remember the integral? It goes what do we have to do? Polar.
Yeah.
So this is going to be 2 cosine theta r dr d theta,
Okay, what about the r?
0 to 1.
What about the second r?
Oh, wait.
It's 1.
Yeah.
0 to 2 pi. And you say this is 0?
Yeah, I lied.
You lied?
Oh, it's still 0.
It's still 0?
Hey, wait. Yeah, okay.
Well, such is luck. So 2 cosine theta r dr d theta. When you integrate r, you get r squared over, so that's integral 0 to 2 pi of r squared cosine theta d theta, computed from 0 to 1. That's just 1. Integral of cosine is sine. Yep, 0. Nice. All right. Well, that concludes this part.
That's it?
Like, usually when it equals 0, we can have the integral, so it would be 2 times and then sine theta from 0 to pi, and then half that again. So it would be 4 times sine theta pi.
That's only computing the area, but we are now computing the value of the integral.
Oh.
All right. Let's just do